Hello everyone, welcome to your first tutorial for ECE 457A. The topic of today's tutorial is convexity, and we're going to go through 4 examples on convexity and their solutions. Then I'll provide some visualization using Python and provide you with the codes for that as well. So let's get started. So, for the first question, we have a convex set. Well, a set is given and we want to demonstrate that this set is convex. So, what we're going to do is to use the definition of the convex set by considering 2 points. Alright, note that A, C are matrices. B and D are vectors, and X as well is a vector n by 1. So if we consider 2 points like x1 and x2, these are vectors. So based on the definition, we have ax1 less than or equal to b and cx1 equals d. We also have ax2 less than or equal to b, c, x2 equals d. Alright, so now we're going to consider a like a scalar alpha in the range or in the interval 0 to 1. So we need to show that like both this inequality and this equality satisfy the convex definition. So going with the first one, use another color. A alpha x1 plus 1 minus alpha x2. This gives us, so alpha is a scalar, alpha x1 plus 1 minus alpha x2, and we know that ax1 is less than b or less than or equal to b. So we can say ax1 is less than alpha ax1 is less than or equal to alpha b, and we also know that ax2 is less than or equal to b. Therefore 1 minus alpha ax2 is also less than or equal to 1 minus alpha b. So overall we can say that this whole term is less than or equal to alpha b plus 1 minus alpha b, which is b. Therefore, this term here is less than or equal to b and satisfies the definition of convex set. Now we're gonna go do the same for the other condition, which is this equality. and I'll do it in the next page. Okay, so let's continue. We have C. Oops, sorry. We have C alpha x1 plus 1 minus alpha x2, which equals to alpha is a scalar, C is a matrix, x is a vector, plus 1 minus alpha is a scalar. Again, C is a matrix and x is a vector. And we know that Cx1 is equal to D, and also Cx2 equals D as well. Okay, so we're going to replace these two terms with D, alpha D. D is a vector plus 1 minus alpha D, which is equal to D. So this condition also satisfies. So we can say that alpha x1 plus 1 minus alpha x2 also exists in the set. So it is convex. And that's it for this example. So for the second question, we're gonna check the convexity of a set again. So this is a set given to us, and this is a condition on the set. Based on the definition of a convex function, we say that, like for f of x, f as a function of x, to be convex, the definition says that f of alpha like x1 plus 1 minus alpha x2 must be less than or equal to alpha f of x1 plus 1 minus alpha f of x2. So here f of x is the norm, and in the previous example we actually had two functions. The first one was like a matrix multiplied by x, and the second one was another matrix C multiplied by x. So here we have the L1 norm. Alright. So using the definition, we have to consider 2 points again, like 2 vectors, x1 and x2. Again, vectors. And alpha a like scalar value. Okay, so we say that for the first point we have x1 less than or equal to 1, like L1 norm of x1 and L1 norm of x2 less than or equal to 1 again. Now we're using the definition given here, this one. So this is a norm function. So L1 norm is our function. So we say that alpha x1 plus 1 minus alpha x2 L1 norm must be less than or equal to let me continue that down here. L1 norm of alpha x1 plus L1 norm of 1 minus alpha x2 which is equal to, because well alpha is a constant, is a scalar, and it's also positive because we mentioned that alpha must be in this interval. So we don't need to use the absolute value sign. We say alpha L1 norm of x1 plus 1 minus alpha, again a positive scalar, L1 norm of x2. Now we know that the L1 norm of x1 is less than 1, and L1 norm of x2 is also less than 1 here. So we can conclude that this term is less than or equal to alpha, and this term is less than or equal to 1 minus alpha, and the whole term is less than or equal to alpha plus 1 minus alpha, which is 1. So the whole term is less than or equal to 1. Therefore, alpha x1 plus 1 minus alpha x2 exists in the set, so we can say that the set is a convex set. And that's it for this question. So before moving on to the next two questions, which are the convexity of functions, I want to talk about something else. Alright, so in the previous example, I somehow demonstrated that we're kind of using this for convex set, which is somehow different from this one, but I just wanted to mention that you can somehow relate them or give you some kind of understanding that they can be somehow interchangeable. So but remember that the definition for a convex set is different from the definition of a convex function, but we somehow did that in the form of a convex function, which is also like true. So for the next two questions, we're going to use definition number 1, 2, and 3. I'll like provide you with 3 solutions for each question, and we're going to see that each of them produce the same result. Alright, show that the following function is a convex function. Solution number one. Solution number one uses the first definition. Let's consider 2 points, x1 and x2, and also a scalar alpha in this interval. And based on the definition, we say that f of alpha x1 plus 1 minus alpha x2 is equal to alpha x1 plus 1 minus alpha x2 to the power of 2, which gives us alpha 2 x1 2 plus 2 alpha 1 minus alpha x1 x2 plus 1 minus alpha to the power of 2 x2 2. So we know that x1 is not equal to x2. Based on this, we can say that x1 minus x2 raised to the power of 2 is greater than 0. So x1 2 plus x2 2 minus 2 x1 x2 is greater than 0. Therefore, x1 2 plus x2 2 is greater than 2x1 x2. Alright, so let's continue that on the next slide. Okay, so we said that x1 2 plus x2 2 is greater than 2x1 x2. We can show that like 2x1 x2 less than x1 2 plus x2 2. Now on the other hand, we know that f of alpha x1 plus 1 minus alpha x2 is equal to alpha 2 x1 2 plus 2 alpha 1 minus alpha x1 x2 plus 1 minus alpha 2 x2 2. And we can say that based on this, we can say that this one is actually less than yes, so this one is less than multiplying this term, the above term, by alpha 1 minus alpha gives us alpha 1 minus alpha x12 plus x22. Therefore, alpha 2 x12 plus 1 minus alpha 2 x22 plus 2 alpha 1 minus alpha x1 x2 is less than alpha 2 x12 plus 1 minus alpha 2 x22 plus alpha 1 minus alpha x12 plus x22. Now we can say that continuing with this part, we can say that that part is equal to, hold on a second. Is equal to alpha 2 x12 plus okay, let's expand this. That will be x22 minus 2 alpha x22 plus alpha 2 x22 and plus, that would be alpha x12 minus alpha 2 x12 plus alpha x22 minus alpha 2 x22, and I hope that I'm correct in here. Okay, so this equals to, let's see, we can cancel this and this together. Do we have any alpha 2? Yes, this and this. We will end up with x22 negative 2 alpha x22 plus alpha x12 and alpha x22. Okay, let's see. Yes, so we can write this as alpha x12. Here we have 1 minus alpha, like this term, and this term. 1 minus alpha plus 1 minus alpha x22, which is basically alpha f of x1 plus 1 minus alpha f of x2. Therefore, we can say that this function is convex. Now let's solve this question using the second definition. Let me use another color, light green. A light green. So for the next definition, solution number 2. So we know that x1 and x2 are not equal, and we need to show that this condition f of x1 greater than or equal to f of x2 and plus the gradient x2 transpose and x1 minus x2. Okay, so we have, based on that, we can say that f of x1 is x1 to the power of 2 greater than or equal to x2 to the power of 2 plus the derivative of that function. So it's 2x, and with x2 as the input, it will be 2x2 multiplied by x1 minus x2. This leads to, let's see, x1 to the power of 2, x2 2 plus 2x1 x2 minus 2x2 2. This would be negative x2 2 plus 2x1 x2. The whole thing will be x1 2 minus 2x1 x2 plus x2 2, and yeah, we can say that x1 minus x2 to the power of 2 is greater than or equal to 0, which we know that it's actually greater than 0 because x1 and x2 are not equal. So this is true, therefore this function is convex. Alright, next let's go to the next slide and use the third definition. I'm going to use color blue for this one. So S3. This will be short, so we have f of x, which is equal to x2, and we show that the derivative is, or partial derivative, is 2x. And we move on to the second derivative, which is 2, and 2 is positive for every x in R. Therefore, this function is convex. Okay, let's move on to the last question. Okay, so show that the following function is a convex function. First of all, x and a are vectors and b is a scalar. So when we have a transpose x, that will be a scalar. Okay. For example, if we have a1, a2, and xy, that will be a1x plus a2y, which is scalar. To show that this function is convex, first solution, first definition, and color red. We say that f of, first we need to consider 2 points, x1, vector 1, and x2, vector 2, and alpha a scalar in the interval 0 to 1. So alpha x1 plus 1 minus alpha x2 is equal to a transpose. Okay. Alpha x1 plus 1 minus alpha x2 plus b, which is alpha is scalar, so alpha a transpose x1 plus 1 minus alpha a transpose x2 plus b. Now we can say that let's add plus alpha b minus alpha b, which is basically 0, so we did nothing. Let's add plus alpha b minus alpha b to this expression. This will give you alpha a transpose x1 plus b and this b with this negative alpha b creates a 1 minus alpha multiplied by b. We have 1 minus alpha multiplied by a transpose x2, so we can factor that one out, plus 1 minus alpha a transpose x2 plus b, and this one is f of x1 and this one is f of x2. F is a function of x1 plus 1 minus alpha f as a function of x2. So the function is convex. That's for the first solution. So in continuation of the first solution, something funny that happened was that we reached to this conclusion that alpha x1 plus 1 minus alpha x2 is equal to alpha f of x1 plus 1 minus alpha f of x2. And in the definition of in the first definition of a convex function, we have that this term must be less than or equal to this one, and we only satisfy the equal part, like equality part. The thing is, ax plus b is a line, and a transpose x plus b. So here a, x, and b are scalars. Here a and x are vectors, and b is a scalar. So in here, this one is a plane. So for a plane to be like convex, it means that the 2 points must be inside of the plane, like on the plane. Therefore, we have only the equal sign. But if we had like 2 planes, the 2 points must be between them or on them. Therefore, we would have we would have these less than or equal sign. So this is just extra explanation that I want to mention about this solution. Now let's move on to the second solution. Let's use color green. X2. So we have 2 points, x1 and x2, which are not equal, and we need to show that f of x1 greater than or equal to f of x2 plus this derivative transpose x1 minus x2 . Alright, so f of x1 is a transpose x1 plus b greater than or equal to a transpose x1 x2 plus b plus the derivative with respect to x. So it's a transpose x1 minus x2, which shows that this term is a transpose okay, you can cancel a transpose x2 here with this negative a transpose x2, and you'll end up with a transpose x1 plus b. So yes, a transpose x1 plus b is equal to a transpose x1 plus b. Therefore, this function is convex. Again, we reached the equality sign because of the definition that I provided here. Let's move on to the next slide and show you the solution number 3 using the third definition. Alright, for solution number 3, we need to take the derivative of that function twice. F of x is A transpose x plus B. Derivative of f with respect to x is A, and the second derivative of f with respect to x is 0, which is actually equal to 0. So we needed that to be greater or equal to, but it's equal to. Then again, based on the explanation I gave you in the previous slide. So this is true for all x's in R. And that's it for solution number 3, and that's it for today's tutorial.